ahead and start this show. So students, this is the last time where you're going to have a time to really pester Kadden with questions. So obviously he ran last week and you're going to see him at least some throughout this week. So Kadden got his degree, in fact, doing mathematics with some knowledge about chemistry before seeing at least something similar to the light and moving to Cornell and doing a PhD in theoretical physics. So that was with Eric Mueller. And actually, in much the same way that I really respect the kind of questions that I was asking James in the previous talk about how do you really know you understand something, you get a similar sense when you talk about people from Eric Mueller's group about being able to describe something fluently using a minimum of exhaustive fancy concepts. And it might not be constrained to two-level atoms in classical physics, but I think the moral content is the same. But since this is the last time we're going to see Kadden in this concept, I'd like to ask you, Kadden, is there anything that no one knows about you that you'd like to tell these students before we move on and see your talk?
Wow, that's quite the thing to spring on me, Ian.
So I'll do one right now while you're pondering, okay?
You'll do.
So I think no one here knows that I was the captain of the Caltech Karate Club as a graduate student. And let my aggression out really nicely. So.
Do you still do it?
No, I had children.
No. You could teach them karate. Yeah, let me ponder and get back get back to you on that. I think that we had in our introductions on the first day, I had shared with them that for fun, do some musical things, play guitar and record songs and write songs. But now I'm trying to think of the PG-13 things that I can share, the family appropriate things that I can share that people don't know about me, and I'm not sure. But
yeah, that's right. This is on YouTube, so keep it at PG-13 or lower.
Yeah, maybe just PG, I guess.
All right. So anyway, Kadden, I'm really looking forward to your seminar, more about synthetic dimensions and all kinds of fancy stuff. So take it away.
Great. So let me share my screen. You can see, are you seeing the right screen? Can you hear me?
We're not seeing screen.
Oh,
yes.
Okay. So let me try again. Okay, I think I know why, because I didn't share it properly.
Success.
Is it the right screen or the presenter screen?
It's a screen with only one slide on it.
Awesome. Right. Okay, and the audio and everything's good?
Yeah.
So far, so good. I'll mute you anytime.
So thanks everybody, and thanks Ian for the really nice introduction. I have a story about, so he had made some nice comments about the Mueller group, and I don't know about the whole group, but definitely Eric is impressive in cutting through sort of formalisms and getting at the essence of things physically. I have one story where I think I had spent a week. I was really proud because I had taught myself a lot of diagrammatic perturbation theory and Matsubara sums, and I calculated some transport through a wire. I came in and showed it to him, and he just goes, I don't know anything about, Matsubara sum, so let's just calculate this. And it took him about 5 minutes. He wrote down some not quite classical, but almost classical equations of motion and reproduced exactly the result that took me a week in a much more illuminating way. So, I think we got the same sense from some of the things that James and others at the school have talked about. You really can, the formalisms are nice, but you don't want to get lost in the formalism when you're thinking about the real world. So here I'm not going to tell you about the real world. I'm going to tell you about a synthetic world, which we've got a taste of from Ian already, in which my results will be very closely connected. So if you understood, understood what Ian was talking about, you'll understand very well what I'm talking about here. Before I dive in, I do want to say that it's a shame we're not in person. So we will run into each other at conferences and things. Please come up to me, introduce yourself, or remind me who you are. I'll probably recognize your face, but if you look very different in person versus on Zoom, you may have to remind me. And I'll buy beer or coffee or whatever needs to be bought, and we can chat more. So, so let's see. So, I don't know why my slide isn't moving. There it is. So, I took a poll on Discord to see what I should talk about today. And the majority of you said I should talk about synthetic dimensions. So that's what I'm going to talk about. But since 1/3 of you, you have to subtract 1 from all these totals for technical reasons. One of you, so about half of you, a third of you had said I should talk about SU, and I put in one slide on SU. So hopefully this won't get us too distracted, but I do just want to whet your appetite for this very fun stuff. So here's a cartoon of some of the fun things that happen with SU in physics. And we heard about this n=2 case a lot at this school, right? So I'm drawing a plane of n, that's the n of SUn, not the number of particles or something. That's on the x-axis, and the vertical axis is the doping, by which here we just mean the filling. How close to one particle per site are we? So, at one particle per site, we heard about anti-ferromagnetism in the usual SU2 model. That's this blue-yellow checkerboard pattern. And we heard that maybe if you dope the system and move it away from n=1, average density 1, you might get a D-wave superconductor or maybe other fun things. And we heard about strange metals and pseudo-gaps and string order and all this fun stuff. So the story for other n is also interesting. So Anna Maria told us all about the SUn symmetry, and but not so much in the Fermi-Hubbard model, but she told us that there are these n-component systems. These n-components all had the same interaction strength. So that's why I'm not even bothering to write down this Hamiltonian. You all remember the Hubbard Hamiltonian, I hope. There's tunneling and there's this on-site interaction. So it's identical when you do the SUn Hubbard Hamiltonian. It's just that when you have particles on the same site, they still interact like they did before, and they don't care which pair of colors you put on the same site. If I put blue and yellow on the same site, it costs the same energy as if I put red and green on the same site. But other than that, the Hamiltonian's just the same thing you'd get for the SU2 case. And so people have studied this model. It was originally studied by condensed matter theorists, or some variant of it was studied by condensed matter theorists in the late 1980s. And then closer to the modern variants, people have been studying intensely, motivated by the prospect of seeing some exotic magnetism. And so this exotic magnetism, I've sort of put some cartoons of what you get on this slide. So it's been predicted for, did I lose the references or did I just put them in a build? Okay, I'll put the references up on here. I think I deleted them on this slide. So it's been predicted by like Frederic Millat and André Leukli and others that you get different sorts of ordering patterns when you increase n. So n=3, you get this kind of stripe order. Let me pull up my laser pointer. Can you see the laser pointer? Yeah, okay, good. So you get this kind of red stripe diagonal with a blue stripe diagonal adjacent to it with a yellow stripe diagonal adjacent to it. And then this just repeats. And so that's the kind of order that you get for SU3. And you'll notice that what's happening is something very similar to SU2. That just like SU2, the blue and yellow didn't want to sit on the same site, but they do want to sit next to each other. You have a similar pattern for SU3. So the red doesn't want to sit next to other red atoms. It wants to sit next to either a yellow or a blue atom. And this is something that using the things you've learned in this school, you can understand very easily as well. So we heard about super exchange as driving anti-ferromagnetic correlations for n=2, but I will give you just a very simple physical reasoning that applies for any n. So these are fermions, remember. If fermions are in the same state, you have Pauli exclusion, so they can't pass through each other. So that means the particles can't move very far. But now, if I'm in different spin states, Pauli exclusion doesn't apply, and I can move through each other. That means the particles delocalize further, and when you delocalize in quantum mechanics, you lower the energy. So this means that adjacent particles will want to sit in different spin states so they can delocalize a lot, and that will be the ground state. And that's why you get this kind of, I'll call it anti-ferromagnetic ordering, even though it's this stripe pattern, that adjacent sites want to be in different colors. And then things get more interesting when you go to SU4. You get these kind of valence bonds. So this stripy oval thing is a singlet, an SU2 singlet, meaning just like you would have down up minus up down, here you have blue yellow minus yellow blue sitting on that bond. And so you break the translational order by putting these valence bonds everywhere. But you also break some spin rotation because this bond is blue and yellow, the next bond is red and green. So there are actually two very different types of physics going on here. It's not just like stripes, it's you're making these valence bonds, and then the colors associated with these valence bonds alternate as I move through space. And then SU5, this is actually some ordinary symmetry breaking pattern, but you can see it's not very simple. It's actually hard to see what the pattern is there. Yeah, okay, so sorry, somebody was direct messaging me. And so just mentioning that there's some garbage on the right hand. Don't worry about what's on the right hand. This was just me being lazy and cleaning up my slides. So, so for SU6 and higher, it's actually not known what happens to this system. There are some approximate treatments, although these are approximate treatments that become exact in a specially constructed limit of the model, not the physical limit, but some other limit, by Anna Maria and her co-authors, Michael Hermelli and Victor Garari, that say that you get chiral spin liquids here, which is a very exotic topological state of matter that's been predicted since the 1980s, but never observed in any system. So you don't need to understand any of this. I'm just trying to tell you that SUN is really rich and interesting, even relative to the SU2 case, right? So the SU2 has this anti-ferromagnet, which is fun, but actually fairly boring. But already at the magnetic level, the SUN system is really rich and worth studying. And when you dope the system, there's been almost no theoretical work on the SUN case. Okay, so in the SU2 case, we may not have the answer, but there have been many, many studies and a lot is known about what happens when you dope the system. The same thing is not true for SUN. So my group, and in particular, one of the summer school students here, Eduardo Ibarra Garcia Padilla, has worked a lot on pushing forward our knowledge of this. So trying to understand what happens when you move away and dope the system, what happens when you move away from the strongly interacting limit, what happens at finite temperature, all of these things. And it should be said that the pictures I'm telling you, they're pretty solid for things like SU3, but as N gets larger, the numerics gets harder, and you may be more prone to wishful thinking on the part of theorists. So it's nice that we have chiral spin liquids on the right, but maybe it's not a coincidence that's where the numerics is the least under control. All right, so we'd like to clarify this situation. So other than just kind of introducing you to this idea that there's a fascinating world of Hubbard physics for SUN, and that it's been realized in experimental labs like Leonardo Filani's lab and Yoshiro Takahashi's lab and Emmanuel Bloch's lab, what I wanted to advertise is that one of the latest bits of experimental progress comes from a collaboration we have with Yoshiro Takahashi that you can find detailed in this paper here, in which for the first time people have measured the nearest neighbor correlations, precisely this anti-ferromagnetic tendency of atoms wanting to sit in different spin states on nearest neighbors. And so this is a plot showing that. It's a plot showing that anti-ferromagnetic tendency for nearest neighbors is a function of the entropy of the gas. And you see as you get colder, those correlations increase. You also see there are two curves here. So the blue curve is 1D, the green curve, is n equal 2, 1D. The green curve is n equals 6, 1D. And you see there's a huge enhancement of correlations for n equals 6. And so I'd be happy, maybe if we have free time or if you want to bug me some other time to explain why that happens. That's pretty well understood. But I think this is telling you that not only is the SU6 physics interesting, this may actually offer in some ways an easier route to accessing correlated physics than the n equal 2 case, because at the same entropies, you can get much stronger correlations, at least for the nearest neighbor. And we could talk about what happens for longer range correlations. So, and that's all I wanted to say about SUN. Maybe if anyone has questions, I'm happy to address these, but otherwise I'll jump into the main topic here. While you're thinking, I'll show my collaborators.
Maybe a quick question. Is there any known difference when one looks at BoseHubbard instead of Fermi-Hubbard?
Do you mean SUN BoseHubbard, or do you just mean scalar? I actually don't know any work on the SUN Bose-Hubbard. Now, there is another connection, which is when you have SUN Fermi-Hubbard, you can ask how many particles can you put on a site, right? If I had spinless particles, I can only have 1 particle per site in the Hubbard limit. If I have SU2, I can put 2 per site. But if I have SU10 or something, now I can have 10 particles in a site. And you might think it actually looks more like bosons, since bosons can also pile up to 10 per site. And there are limits, and this has been explored by like Leonardo Filani experimentally and Gyubong Zhou at Hong Kong experimentally, showing that as N becomes very large, in certain situations, the system actually looks very much like a scalar Bose-Hubbard model, like a U1 Bose-Hubbard model, SU1 Bose-Hubbard model. But I actually don't know much about, even for SU2, I don't know much about the Bose-Hubbard case. But my guess is the physics would be very, very different. At least typically, if you think about how super exchange works, we said for identical particles, If they're identical fermions, they can't pass through each other, but if they're distinguishable, they can. So it wants to delocalize, which causes antiferromagnetism. For bosons, it's actually opposite. Because bosons, if you have distinguishable particles, fine, they go through each other. But if they're indistinguishable bosons, they actually want to bunch up. So I think this drives the system towards ferromagnetism. Certainly in like the super exchange limit where U is much greater than T, you get a coupling that prefers ferromagnetism for BoseHubbard. And that can be engineered and stuff, but that's the kind of default case that comes out. It's an interesting question. Experimentally, you might remember that the SUN symmetry for the alkaline earth atoms only happens for fermions. So I'm not sure how relevant it is for experiments. Maybe if we made dimers or something, you know, if we made Feshbach molecules of alkaline earths, but since we don't have Feshbach resonances there, that's probably pretty tricky. Yeah, any other questions?
I guess a simple question is what's the most premier numerical techniques for studying these problems?
Oh, yeah, so I didn't mention, so actually I only showed you the 1D results here. There's also the experimental results in 2D and 3D, and we've also done calculations in 2D and 3D. You won't be surprised to know that 1D is easier than 2D is easier than 3D for lots of reasons. The premier techniques, if you're at 0 temperature and in 1D, is probably to use DMRG. And if you're at finite temperature, it's probably to use a world line quantum Monte Carlo algorithm. You can ask where one might win versus the other, but you know, but the Monte Carlo can get you pretty cold. For higher dimensions of the system, you know, the numerics is really a mess. So a lot of the methods shown here are either exact diagonalization, you know, that I'm quoting the results of here are either exact diagonalization, or they are like IPEPS methods. So these infinite size tensor network methods. That's just for the magnetism problem, all the results here. So they study the special limit where it's just a SUN Heisenberg model. For the Hubbard model, there's been very, very little work done. So Kongjun Wu has used DQMC, and we've used a different type of DQMC that we developed, a determinantal quantum Monte Carlo, as well as a numerical linked cluster expansion, which hasn't been published, but hopefully there's a draft out to all the collaborators. So hopefully that'll get out real soon. We can share it with you if you're particularly interested. So those, I think, are probably the premier methods based on the analog for the cold atoms kind of circumstances, based on analogy with the SU2 circumstance, I don't know, SU2, what's been observed to work well. So, you know, I think we've seen from Randy, from Wasim, we may see from Emmanuel, also from Tillman maybe, that, you know, DQMC and NLC are really the two methods of choice for doing a lot of calculations. And this is in part because the correlation length isn't super long, so you can deal with some finite size effects that these methods have. Yeah, anyway, for a lot of reasons, those end up being kind of the preferred methods for SU2. And so those are the ones that we've been pushing on for SUN. That said, there are other approaches like dynamical mean field theory. And just, I think it was last night on the archives, somebody did a study of the SU4 Fermi-Hubbard model using dynamical mean field theory. And in Leonardo's recent experiments, he sees something called an orbital selective mod insulator. And I believe they used, well, I'm sure they used a dynamical mean field theory to do some calculations there. Actually, the dynamical mean field theory is probably much more approximate than the kinds of techniques I'm showing here, like the DQMC. But again, it depends on where you push the numerics and what regime you're doing comparisons in. You know, but one-site DMFT in some ways is a pretty crude tool. You know, it captures insulator to metal crossover very well, but capturing things like, you know, these stripe orders, you're not going to get that with a one-site DMFT. You'd really have to, you know, use a larger unit cell. But it's an interesting question. You know, maybe there's some new type of numerics that we need to develop that will capture the SUN very well. And actually that's, you know, so these results here on the screen happen to come from exact diagonalization, but we've truncated the Hilbert space of exact diagonalization very carefully to put in some of the physics of the system. And if you didn't do this, it would be impossible. You couldn't do more than 3 or 4 sites, but maybe 4 sites for this system. And so we can only do 9, but that's like a heroic difference from 4, maybe only 8, but it's a big difference.
And then how quickly do you run into the sign problem with n, like say for fixed dimension?
This is an awesome question. I'm actually tempted. Here, I'm gonna pull up something on Overleaf. I mentioned we have a draft, so let's see if I can pull this off without totally train wrecking everything or giving away company secrets. But my web browser is not started. So while I'm doing that, I'll describe it verbally. So the sign problem, just to recall how this works for SU2. For SU2, there is no sign problem when you have one particle per site, and it only develops away from one particle per site. The same thing is absolutely not true for the SUN case. And the reason is because the sign problem, for whatever reasons, if you're familiar with the method, you'll know why. If not, just take my word for it. The sign problem goes away when you're at half filling. It goes away when you have this particle hole symmetry. And so that doesn't occur at one particle per site for SUN. It occurs at in half particles per site for SUN. And so that's not the experimentally relevant regime, and we always have a sign problem. So it gets worse, certainly at integer filling for that reason. You go from having a sign problem to not having one. But it also gets worse in the kind of metallic regime where you do have a sign problem. So maybe you can see my Overleaf document here.
So Kadden, you said something that confuses me while that's appearing.
Yep.
Which is that there's no sign problem for spin 1/2. So that's saying that spin 1/2 quantum spin liquids are in fact straightforward in quantum Monte Carlo?
There's no sign well, it depends on the spin liquid. So let me go back. So what I said is that if you're at half filling,
okay.
But most spin liquids are predicted at half filling, right? They're predicted at one particle per site. So you're right, that seems a little confusing. So the answer to this is that where you probably get spin liquids is on frustrated lattices where you have other problems, or you may even have a
okay.
Yeah.
So you meant this on a square lattice or in 1D or something like that?
Exactly. So square lattices, you're totally fine as long as it's unfrustrated.
All right.
So it turns out SUN also causes some frustration and things. But so can you see the PDF that I've got pulled up here? Okay. So so this is an evolution of the sign. The average value of the sign 1 means you don't have a sign problem, and as it dips below 1, it means you have a bad sign problem. And there are a lot of curves here, so maybe let me zoom in. And this is all Eduardo's work, so you can pester him with the comments, which he can answer better than I can. But let's just look at this top panel. If you look at the different n, so the circles are n equal 2, and there are 2 rows of circles. There's the sort of solid circles and the open circles here, which correspond to 2 different interaction strengths. So let's just look at the solid circles, ignore all the open circles. So here you see for n equal 2, the sign problem is very, very weak, even away from half filling. Half filling is right at the center here. Mu is equal to 0, 0 on this horizontal axis. And there's
What's
just
the
a little
T
bit
here?
What's that?
What's the temp here?
The temperature is 0.5 times the tunneling. And so that's why the sign problem is not too bad even in the middle. But you see when you go just to n equal 4, which is not that, it's only twice as large of n, you see the average sign is now down to 0.2 in the middle. And even at the 1 particle per site, it's less than 0.4. So 0.2 or maybe 0.1 is where basically the numeric starts to become unusable. Once the sign problem's that bad, you kind of have to run away from it. You don't want to try and overcome that sign problem. So in particular, the statistical error officially goes like 1 over the sign squared. So a average sign of 0.1 would make it 100 times harder. But that's, it's actually worse than that because you can get into non-ergodicity issues and things. Okay. But if you want to know, this is something we've thought a lot about. Where can we do good numerics and where does it suck? So that's a hint of the answers to that. Good. Let me try to pull the PowerPoint back up and hopefully I didn't break it. Okay, good. So we are half an hour into the talk and I've done 1 slide. Feel free to ask other questions. I don't have that many slides. It's okay.
I presume you have 3 slides.
Exactly. Yeah. Right. I'll say what I think every other lecturer has said. I may not get through all of my material today, but we'll get through the important stuff. Okay. So that's that. That's SUN. They're my collaborators. Yoshiro, that's his group. You can go back on YouTube and look at them all. My group doesn't just do synthetic dimensions in SUN. We do other stuff. So let me get started on the synthetic dimensions. So I have 2 sort of bits of topics here that I'm trying to introduce. So we've heard a lot about, or in all of our courses, we've heard about the early years of AMO physics from the 1800s to, it didn't really end at 1990, but let's, sometimes it feels like it does. It feels like forever ago. Just this traditional, like, let's measure spectra really, really accurately. Let's see all the spectral lines we can and measure everything about them. And this is what led to quantum mechanics and led to all kinds of ability to sort of control and measure matter, especially with the introduction of the laser. Let us do all this very accurately with 99 point whatever percent fidelity. And then really something changed or was added to AMO physics starting in the sort of mid 80s to 1990s, whereas we weren't able to just image and control the internal degrees of freedom, but experimentally, I mean, I'm not able to control anything. I control a piece of chalk, but the experimentalists were able to control the motion of the atoms, the position of the atoms, as well as the internal degree of freedom, using laser cooling, evaporative cooling, things that we heard about from Eric Cornell and Wolfgang Ketterle here at this school. And we've seen beautiful pictures like these quantum gas microscopes. That's an example of being able to see every atom. But where I want to go is why not use both of these types of control? And I think that this is actually a little bit of an underexplored area. At least it fits my narrative if I say it is. And this is, sure, people control a lot of times 2-level systems, even 3-level systems like we heard about from Alexei. And I didn't mention it, Alexei is one of the pioneers of all this SUN stuff. But there's, even though we're doing that, a lot of these systems have a lot more degrees of freedom, internal degrees of freedom that we could be utilizing. And a lot of times they're not so experimentally difficult to control those extra internal degrees of freedom. And so that's a frontier that I think is worth exploring. Can we use better both the internal and motional degrees of freedom? And that's where the synthetic dimensions come in. And you've heard about this from Ian, so you have some idea of how this works. So by synthetic dimensions, I just mean matter that behaves as if it lives in extra spatial dimensions, that in addition to the real physical dimensions, there is some other degree of freedom that when you write down the Hamiltonian, it looks like you have a higher dimensional Hamiltonian. So if your real space is 3-dimensional and you have an extra dimension, you have a 4D system, right? Or maybe in real space, you combine everything, so it's just 0-dimensional and you end up with a 1D system from the synthetic direction. But the synthetic dimension is just that extra degree of freedom. And we've worked on multiple different types of synthetic dimensions. I doubt I'll have time to talk about it. So if you're curious, talk to me. But one of these is what are called momentum space lattice synthetic dimensions. And these are pretty remarkable that they work at all. Anyways, yeah, we'll talk about it at the end if anybody's super curious. I think we have several members of Bryce Gadway's group who's really pioneered this technique here in the audience. So you can ask them all the details. But what I'm going to focus on is Rydberg atom synthetic dimensions, or also you can do similar. Yeah, so Michael's volunteering. Michael Hyman is one of the people who is working with Bryce. And so he probably knows a lot about this. So I'm going to focus on this other type of synthetic dimension, which is conceptually quite different about how it's sort of built, or at least technically different. And this uses Rydberg atoms. And you could also use molecules just as easily. Most of the experimental progress so far has been on the Rydberg atom front. And so that's where I'm going to show you real results, but people are certainly working on it with molecules as well. And you can understand these as very similar systems. I like to think about a Rydberg atom as just a diatomic molecule. It's just that one of the atoms of the Rydberg atom is a nucleus and the other atom is an electron. So that's my diatomic molecule. And then all the physics maps pretty well from one to the other. So the structure of this talk has 2 pieces. The first part of this talk is going to introduce the idea of synthetic dimensions and just talk about single particle physics, which, I don't know how interesting single particle physics is, but there's a lot of fun things you can do with it. And at least that's maybe where you want to start before you add interactions to the problem. And then the last part of the talk, depending on how much time we have, we'll definitely talk about what interactions do, and we'll see how much time we can really spend on it. But there are several new features of the interactions in these types of synthetic dimensions that are really, really interesting for us. So there are things like what we call quantum strings or membranes, also what I would call topologically protected models or realization of anomalous models in the sense of quantum field theories. And most recently, this is unpublished, but there are actually hints of fractonic physics if this is the kind of thing you're into. So we'll see how much of this we talk about. let's just start with the internal states we're going to be using. So you're all experts on Rydberg atoms now from all of our lectures, right? And so Rydberg atoms, from our point of view, really the only important thing is that they have internal levels. They have these n equal 40, n equal 41, n equal 42, the different principal quantum number states. Okay, and similarly, you're experts on molecules from June's lectures, and we know that molecules can rotate. And so here is a spectrum of rotational states of a molecule. That's actually an oversimplified cartoon of the spectrum, but it gets the point across, and we can look at more detail later. And nicely, both of these systems, you can couple the different internal states very easily. You don't need to build a laser system for every pair of states you want to control. So there are nice, convenient microwave transitions in both the Rydberg atoms and the molecules. Okay. And we can talk about the detailed structure if anyone cares, the atomic structure of, so hyperfine states, angular momentum states, all the stuff that I may be kind of sweeping under the rug here. Some of it I'll talk about, some of it I won't, but I'm happy to discuss any of it. So let's remind ourselves of what Ian told us about synthetic dimensions. So at least one of our favorite types of dimensions, if you look around, is particles moving in a lattice. Particle is indexed by some discrete location. It can sit on this lattice site or this lattice site. So here we have a particle sitting, whoops, one second. We have a particle sitting here, this blue ball, and in the one band limit, there's just one state it can be in if it's on that lattice site. And if I look at that as a cartoon of it, I'm rotating at 90 degrees for reasons that will become apparent in a second. There are like 4 states here. So I had 4 real space states. In the one band limit, there are 4 sites I can be in. And that looks just like maybe here I have 4 different rotational levels. So at the level of looking at the Hilbert space, there's no difference between this real lattice structure and this synthetic lattice structure. Okay, and this is super boring, who cares? But to say 2 quantum systems are identical, we have to do more than just say they have the same Hilbert space, right? We have to say they have the same Hilbert space and they have the same Hamiltonian. So what is the Hamiltonian for a typical real lattice? Well, we'd have tunneling or something like that between lattice sites. And we can mimic that by just sending in these microwaves and putting a resonant microwave on the transitions where we want tunneling. So if I want a nearest neighbor tunneling, I send in a microwave resonant from 1 to 2. Okay, now here it's really important that both molecules and Rydberg atoms are not harmonic oscillators. They're not like, what we've heard about from James and others. This spectrum is not linear, right? So the spacing between adjacent levels is very different going from 0 to 1 versus from 1 to 2. And that means that we can use different frequencies of lasers, different frequencies of microwaves to drive different transitions. And so you can go send in a bunch of different frequency microwaves and have control over all of these tunnelings simultaneously. And it's probably an oversimplification a little bit, but I don't think a huge one to say that you can go buy something like a direct digital synthesis device, plug it in to your computer and type in whatever set of frequencies you want generated, and they will just come out of your horn. So you can really dial in whatever set of tunnelings you want to use here. Write an arbitrary synthetic dimension. Okay, so that's all well and good. And this is, in some ways, this is very closely related to what Ian talked about. Ian, of course, used Raman couplings to go between these because he wanted to give momentum kicks, but we won't need that. So there's a question from Jaron. It says, does that mean the number of microwave lasers increase proportionally with the system size of the synthetic 1D system? Yes, very, very good. That is exactly right. The number of microwaves you need is proportional to the system size. The good thing is that it's not like lasers. You can really get, if you want to put in 100 different microwave frequencies, it's not a big deal, either in terms of the microwave power or the sort of, generation techniques. I mean, it's simple, off the shelf, cheap hardware. You go put in 3, but it's 20 grand or 50 grand or something, and a little bit of grad student time, and you can go have as many frequencies as you want. There are more technical issues about how does noise come in, how do you calibrate these things, and so I don't want you to think that you just automatically get a million levels if you want them. There are limitations, but it's not in generating the microwaves. And so I'm happy to discuss those limitations a little bit more. I'll even have a slide where I talk about some of those limitations. And so if that's something you're really interested in, we can dig into that. but I don't think any of them will limit us for, say, 10 lattice sites.
Sorry, I think I missed this, but why is it bad to just have a harmonic oscillator and one microwave? I would then
Yeah,
just
so
have a
it's
semi.
not necessarily bad, but what it means is you will not have independent control over all the tunnelings. So you'll get maybe a constant, all the tunnelings will be equal, or maybe there's some matrix element that's described by the harmonic oscillator wave functions, but you won't have that ability to just dial in an arbitrary set of tunnelings, which can be very useful. So so the first difference between what we heard about from Ian and this sort of setup is that we have a lot more synthetic sites available to us than Ian does. So Rydberg, maybe you could, I don't know how far you can push this. I'll show you experiments that did 6, but we certainly were not, that wasn't a real intrinsic limit to these experiments. Those were Tom Killian's experiments. Molecules, they have hundreds of stable states. We heard from June that these can live for, tens of seconds and even maintain their coherence for a very long time. So, so the states are there, that generating the microwaves is there. There may be other issues, but there's potential to grow these a little bit bigger. There are serious drawbacks. The main one being that you don't want Rydberg atoms and molecules to collide. That's a very lossy process. We've heard a lot about that. Ian doesn't care if his particles collide. His particles can move around and do all kinds of stuff, interact, get really cool physics from that. We're limited.
That's, right.
We can't.
That's a bonus.
That's a bonus for us or for you?
For me.
Yeah, that's a bonus for Ian. That's great that Ian can do that on top of everything. That's a bonus. Yeah, gotcha. So Shah was asking how resonant or narrow do the microwaves need to be? They need to be sort of resonant to within however big you can make these tunneling rates, which is set by, if you like, the Rabi frequency. That is at least coming out of the microwave. I mean, it's a total non-issue. I think you're pretty much band limited. So just the length of the pulses you're applying, which can easily be, so if you apply, well,
Gotcha.
yeah, I mean, I think it's just not a limit on the microwave. I think by, many orders of magnitude before you hit that limit, you're encountering things like Rydberg lifetime or other issues.
Thanks.
Mm-hmm. Yeah, but these are all the kinds of things we spend a lot of time thinking about. So in principle, Fourier limited, but I don't know. The other things are going on. Yeah, maybe we'll come back and talk about the sort of non-idealities of these experiments. We're spending a lot of time on this now too. But let me tell you why we want to do this in the first place. So here's a more realistic cartoon of molecules, just to give you some examples of what I mean by you can arbitrarily engineer these things really pedantically. So if I wanted to create a 1D synthetic dimension, I've just circled a set of states that lets me create a 1D synthetic dimension, and I can couple them nearest neighbor to get a nice 1D wire. And you might say, wait, now if I populate these states, won't they just leave the manifold? There are degeneracies and things here after all. And that's just because my cartoon's too simplified. Actually, in the presence of a magnetic field, which these experiments are almost invariably done with molecules, these degeneracies are broken. They're so far off resonant that if you put it in this initial manifold I drew, you'll just live forever in that manifold on the timescales of the experiment. So you don't couple to all these states I'm not circling. You just stay in the states you want. And that's also true for the Rydbergs. You do have to be careful you don't hit an accidental degeneracy or something, but these are not super serious issues. But you could also make a ladder, right? So this is like two 1D systems right next to each other. Like we heard from Thierry about ladders or 3-leg ladders. You can do all of that here as well. Some unique things you can do, maybe not so easy to do in real space, is you can make things like rings. And you can even put a flux through those rings. So I can control not only the tunneling amplitudes, but I can control the tunneling phases. And because I can control the tunneling phases, I can make a gauge field or even a time-dependent gauge field. And you could do things like spin orbit and all kinds of stuff. The on-site potentials are controllable as well, not just the tunnelings, because the on-site potentials correspond to the detuning of these microwaves. So if I detune one of these microwaves, it's the same thing as shifting the energy level. And that's something, came up a lot in Alexei's lecture and other lectures. So you have control of both the on-site and the tunneling. You can do a lot here. You're just limited by how many levels you can play. And for free, you get a quantum gas microscope in the synthetic direction, in the sense that you can resolve what's going on with single site resolution, right? So if you want to know how many Rydberg atoms are there in state, 41 versus 42. There are things like selective field ionization, and I'll show you results from that let you address this. Doing it locally in real space as well would be a challenge, but just doing the synthetic imaging is possible. Molecules, it's difficult to simultaneously get the populations of all the rotational levels, but you can pick one rotational level and get its population experimentally. So in that sense, you have, it's very much like a quantum gas microscope. So if you wanted to, you dial in, like I said, you just type in what microwaves you want. You could just go one by one, go through this whole topological periodic table that Nigel Cooper mentioned to us, that we can classify every possible topological band structure, and we can just type in all the ones we can want. Making the 2D and 3D ones gets tricky because we don't have that many levels, but definitely the 1D ones we could just go explore. Some of these require particle number non-conservation, so we couldn't do those in an obvious way, but the other ones we could. And I'm just going to focus on one of these. I'm going to focus on the SSH model, which we've already heard about, because that's where it sort of as a proof of principle, I'll be able to show you some experimental results realizing SSH using this technique. Okay, that's kind of I would say the background ideas of the synthetic dimensions. Is this all clear, or do you want me to clarify some stuff before going into the physics of the model? Okay, I got at least a couple thumbs up there, so I'm going to keep going. But do interrupt if anything becomes unclear. So you saw SSH. So I'm just going to real quickly remind you of how SSH works. We have strong tunneling. It's a 1D chain with strong tunneling, weak tunneling, strong tunneling, weak tunneling. And there are no on-site potentials here. And if you go diagonalize this, you can do this analytically. What you see is that there's a valence band and a conduction band. So there are two bands of delocalized eigenstates that just delocalize over the whole system. And then there are these two very special edge states. And these edge states occur at exactly zero energy, at least in the limit of an infinitely large chain. And even if you perturb the system, as long as you obey the chiral symmetry that this has, you will not break the degeneracy of those edge states. Okay, and so that's what we meant by the topological protection. And that's, I think as an AMO person, it's very relatable to understand why would you want a topologically protected edge state? Well, as AMO people, we love two-level systems, and we love our two-level systems to be robust. This is a way of giving you a two-level system that is completely robust to noise and disorder. The fluctuations, the splittings of those states are exponentially small in the system size. And if you're curious, we could, this is a very simple example that I think Nigel worked through, and we could go into detail why this happens. But if you don't remember, that's fine as well. Just take this as a given that this does happen. Okay, so here's my challenges slide. I promised I'd put some of these up and we can go into great details. So I've glossed over the rotating wave approximation. I said that we could move to the rotating frame, and tunnelings and the microwaves would look like tunnelings, but this is neglecting counter-rotating terms. Fortunately, that looks like it should be good to like maybe 1 part in a million or something. So we're not too panicky over it, but we are putting in a lot of microwaves. Maybe the effects accumulate or something. How do we detect these things? What are we looking for? What about off-resonant levels? Those were simplified level diagrams I was showing you. So are the off-resonant levels going to cause problems? And of course, in the eminent scholar Donald Rumfeld's terms, what about the unknown unknowns, the things that we weren't smart enough to think of, right? And so I could sit here and we talked for 10 minutes why I think this would be okay. And when we first published about why we thought this would be okay, we went into some of this. But I think better to show you is to just show you the experiments. I will show you that the proof is in the pudding. People have done the experiments and they work. And I'll start real quickly by telling you what's happened in molecules, and then move on and tell you what about the Rydberg experiments where there's been more done. So Simon Cornish's group at Durham has really pushed the molecules the furthest, sort of the technologies you would need to realize this synthetic dimensions. And they've done coherent control of up to 6 rotational levels. So all the way up to the 6th manifold of those rotational states. And they haven't done 6 simultaneously, so they haven't made a 6-site synthetic dimension. They've done them in pairs for just reasons, very technical reasons about what they can do with their microwave generator. But they're, this is, easy to get around. And the next step is to couple a lot of these at the same time. There have been experiments by the Jia group, I think is the name, in China, where they've done 3 sites simultaneously. They didn't use the phrase synthetic dimensions. They called it Outler-Towns, which is a famous quantum optical phenomena, but actually Outler-Towns is just a 3-site SSH model. So they've demonstrated this in molecules as well. So I think the prospects for molecules we're right in this regime where we have all this necessary coherent control. You can start doing synthetic dimensions, but people haven't really seen, well, more than 3-site synthetic dimensions yet in this case. Where there's been a little bit more progress is on the side of Rydberg atoms. And so my colleague Tom Killian here at Rice, as well as Bryce Gadway at the University of Illinois, have both been working on the Rydberg atom synthetic dimensions. And I'm going to show you, Tom, the results that we've got with Tom. So here's a cartoon of his experiment. We have a BEC of 84 strontium located in between some plates, and we send in our microwaves and some lasers, and then we're going to be able to do to ionize these atoms and use the electrons that get stripped off to detect which Rydberg state they're in. If you don't care about any of those details, none of that matters. You can think about it like a theorist would, like I do. We've got this set of levels that we're using as our synthetic dimension. The set of levels that we picked was 57s, 57p, 58s, 58p, 59s, 59p. Those are our 6 levels. And then we couple into that 6-site manifold from the ground state using a 2-photon transition. So that's going to let us sort of just spectroscopically probe the 6 sites making the synthetic dimension. Right, so you should think about, we've got a 6-site synthetic dimension and then some auxiliary field, which is just what we couple in from to probe the synthetic dimension. And you can see what I've drawn here. This is the SSH Hamiltonian, strong bond, weak bond, strong bond, weak bond. And it's in what we would call the topological configuration, right? Because I can put the strong bond on the edge or not. And here I've got the weak bonds on the edge, and that's where you get the edge states. If you had the strong bonds on the edge, you would not get these edge states. You may remember Antoine had mentioned getting SSH in his tweezer experiments, which is extremely interesting, but also extremely different from how we're doing it here. That was all in real space. This is all in the synthetic space. Okay, and this is all single particle physics. We're just going to excite one Rydberg atom and let it move around in this level. So remember, this was the cartoon. We have our valence and conduction bands, and we have these 2 edge states. And for reasons that will become apparent, I want to rotate this. So just this is the picture you're supposed to have in mind. Now energy is on the horizontal axis, so there should be edge states at 0 energy, and then these bands out on the wings. You go do the experiments where we're going to couple in the data I'm showing you here, couples into level 5. So the probe is near resonant with level 5. And you do get, in fact, these 2 bands exactly where you'd expect them. So, and that's the valence and conduction bands, if you want to think about it that way. So that's great. You might wonder, why don't I see the edge states? Does anyone have thoughts on why I don't see the edge states?
Maybe you're not coupling to them.
You're not coupling to them. That's exactly right. So what you should do, you should get resonances when you're on resonance with an eigenstate, but the amplitude of that peak that you see is going to be proportional to the wave function squared of sitting on the state you couple into. That's what controls the weight of this. So if the edge states have very little weight on I = 5 on the 5th side of the synthetic dimension, you won't see a peak, right? And so just to show you the weights, that's what I'm showing here. So this gives you the vertical axis is the lattice site, and beta = 1 is the first eigenstate, beta = 2 is the second eigenstate, da, 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 da. So the edge states are clearly beta = 3 and 4. You see they're all localized on the edge, and they have almost no weight on the lattice site 5. Okay, and so that's why if your probe, if you're coupling near resonant to site 5, you're not going to be able to excite those eigenstates. However, if I excited to 1, or actually even 3, you see there's a little bit of admixture, maybe I'd be able to see those edge states. So Tom went and did the experiments for all different values of the probe, the states that we could couple to. So those were 1, 3, and 5. And so the state 1 is this blue curve in the middle. And indeed, you get a nice 0 energy peak when you couple right to the edge where you have a lot of weight on the edge. So you can probe the whole spectrum, and all of the weights and all of the peak locations agree exactly with what you expect in theory. Now you'd see you still might say, wait, shouldn't I probe = 3 have a little bump here? And the answer is it's just too small to see here. If we go to different configuration, this is just a smaller ratio of weak to strong bonds. You do see that curve starts to develop a little peak here. Okay, again, all of the weights and positions are exactly where they expected. So that's the topological configuration. You see the edge mode. What if you go, as a sanity check, you want to make sure you don't see edge modes when you go to the topologically trivial configuration. So you have the strong bonds at the edge.
Why is there not the sixth one here? I guess, is it there?
You mean, why is it only 135 and not 246?
Yeah.
Or something else? Just because of dipole matrix elements, you can only couple into the S states, not to the P states. Yep. You might be able to do a 3-photon transition or something like that if you wanted to couple into the P states. We've talked about this. Anyways, that's it, just dipole selection rules. Okay, so this is the topologically trivial configuration, and all is well and good. We get our same sort of valence and conduction bands, but no edge states, exactly as we expect. And remember that robustness to disorder? We can apply disorder to our system and see if it's really robust. So in the upper right, this is the ideal case with no disorder. And the two curves, again, are two different probes that we're using, right? Different probe states that we're coupling to. That's just for scale, to remind you of what it looks like without disorder. Now, this curve in the sort of blue and purple on the bottom right, it has 15% disorder. So if the nominal tunneling is 1, we're now letting the tunnelings go from 0.85 to 1.15. And you see that that edge state, this is zoomed way in, is almost entirely unaffected by those kinds of perturbations. It is robust to disorder exactly like it was supposed to be. And now even here, you can do another sanity check. You can say, maybe, I don't know, maybe you forgot to turn on the disorder. Maybe your microwaves missed the chamber or something like this. So what you can do is, remember, the topological protection is only when you're in the right symmetry class. And if you break that symmetry, then you should lose that robustness. So they send in on-site potential disorder, not just the chiral symmetric disorder, which is tunneling strength disorder, but on-site potential disorder, and you see it totally wrecks the edge state. So everything is behaving exactly as expected, and again, in good agreement with all the theoretical expectations. Okay, and then this is just a picture to show you that not only can they see these spectra, but they can actually go on resonance with one of these spectra and see what is the composition of from the different synthetic dimensional sites. This is the quantum gas microscope. This is telling us the number that we have in the 59P state, in the 59S state, in the 58S state, and the 57S state. Okay. And so this is extremely encouraging to me. Again, these were very sort of initial experiments, but they worked just as well as you could hope for. And this was with 6 sites, but there's no, we went 2, 4, 6, and we've done modeling, and there's just no reason to think that you couldn't do 8, 10, 12, who knows where it stops, but we can definitely go bigger. So, so I think in terms of the non-interacting stuff, that's really a good place to pause. I'm going to tell you what happens with the interactions in the last half hour or whatever we have, but this is the sort of non-interacting conclusions. I think experiments are really starting to see this stuff now, and we are able to control these internal states. The next steps are to look, even at the single particle level, there are these things like high order topology, there's flow K topology, and there's topology in the presence of dissipation and open quantum systems. And I think we've heard a little bit about all of these things, especially the flow K and dissipation from Nigel and Sebastian. And some people have mentioned the higher order topology, but I don't remember if anyone's really talked about it. But these are all very exciting directions that aren't as well understood even at the single particle level and can all be played with here experimentally. So let me stop for questions there before moving on to the interactions. Or I can just move on to interactions. Okay. Interactions. So, so there are lots of things that interactions can do. So one thing that gets tricky to keep in mind is that there's sort of an infinity of experiments you could do, or infinity of systems you could create, because you have this total control of the single particle band structure. So if there are 100 different single particle band structures, the effects of interaction may be different in every one of those cases. Right? And I also have control over the real space structure now. So with the interactions, I'm going to be thinking about not just one particle, but I'm going to put them around in real space, and I'm going to have both that geometry. So obviously I can't tell you about all the thousands of combinations that gives rise to. I'm going to focus on, by and large, the simplest setting. So the first direction is this direction of strings and membranes, which arises even in the case where you just have uniform tunnelings. So forget SSH, it's just all the tunnelings are equal to each other. And then I'll tell you a little bit about these topologically protected models where it's SSH plus interactions. Okay, so let's start with the strings and membranes. It sounds very exotic. Quantum strings, I think we once got a referee who might have been a string theorist, or anyways, it was somebody who was complaining that the math we used was too old. He said that, you know, this paper doesn't use any math from before the 1950s or something, or from after the 1950s. And I wasn't quite sure why that was a criticism, but I'm just going to guess it was a string theorist. Okay, we know how interactions behave because it's been covered in this summer school, both for Rydberg atoms and molecules. And so I'm drawing it for molecules, but it's almost identical for Rydberg atoms if I imagine these are different angular momentum states, right? So I know this is SPDF. We know that there's this resonant exchange process where one particle increases its angular momentum and the particle adjacent to it decreases its angular momentum. So here I'm just starting with two particles. I have two lattice sites, one particle per lattice site, you know, one molecule or one Rydberg atom per lattice site. And these two particles are just going to swap their angular momentum states. And importantly, the following processes are not allowed. That's just dipole-dipole, right, from what we've seen. These processes are not allowed because they're far off resonant. I could have a process like here, where the dipole matrix elements say both particles can lose angular momentum, but the splitting of those energy levels is so large compared to the interactions, that's like just not going to happen. That's, you know, a factor of 1,000 or 1,000,000 off resonance. That's not going to happen. 1,000. There are other terms that are off resonant for similar reasons. Imagine I had a P state and a P state. They could go to an S state and a D state, right, in the Rydberg atom context. But because this is not a nonlinear spectrum, this also is off resonant, unless you happen to hit something called a Förster resonance, which was also mentioned by Antoine. So there are special cases where you just coincidentally get a nice resonance here, but you can avoid these things. Okay, so we're going to ignore those terms because they're off resonant, and all that's left is this flip-flop when you're in adjacent levels. Okay, and then the other thing we're not going to do is we're not going to let particles tunnel. If particles move around, I mean in real space, because if particles move around in real space, you're in trouble. They'll collide, they'll get lost from the trap. They'll react if they're molecules or do bad. They'll also react if they're Rydberg atoms. Lots of bad things can happen. So we're going to stick them in place. And now if you did this with rubidium, like in Ian's experiment, you'd be done. Nothing interesting could happen because the particles just wouldn't interact with each other if you froze them. But because of the dipole-dipole interaction of Rydbergs or molecules, even when they're frozen in place, they can still interact and have interesting dynamics. Okay. So that's what we're relying on. And so maybe here I can also say that this is very different from Ian's experiments in another way, and it has to do with the structure of interactions. So in Ian's experiments where he's using rubidium, all of the atoms in synthetic sites talk to all the other synthetic lattice sites at the same point in real space, but they talk sort of infinitely long range in synthetic space, right? So if I call the states, you know, -1, 0, and +1, 0 talks to 1, -1 talks to 1, you know, -1 talks to 0. All the pairs interact, and they interact almost equally. And even if you use some of the things like potassium with a spin 9½ or whatever, they still have this very long range, sort of infinite range interaction in the synthetic dimension. And that's very different from most real dimensions, right? And so that makes it interesting because it's very different from real dimensions. But if your goal is to see, you know, some types of physics, you're not going to get it with those types of interactions precisely because it doesn't have this local structure in the synthetic dimension. In contrast, this dipole-dipole interaction is actually local in the synthetic dimension. This flip-flop between S and P going to P to S, that only happens when you're at adjacent angular momentums. I don't have S and D going to D and S. That's, you know, so the angular momentum can only differ by 1. So you actually get this locality structure. And so that's an interesting difference besides, you know, if I say we have more levels, that's great, but this is a real, I'd say more fundamental, more interesting physical difference between the two setups. Okay, so if we lose something by not being able to let the particles move around and tunnel, I think we gain something by this interesting interaction structure and maybe having more levels. Okay, so that's, if you want to write it in a particle notation, that's just what the Hamiltonian is. We can generalize this beyond two particles. The mental picture I want you to have in mind here is something like an array of traps. This could be an optical lattice, or it could be optical tweezers or whatever. And then there'd be all these synthetic states in the for each of these traps, right? So it's like one real and one synthetic gives me a two-dimensional system. And we could also consider two real and one synthetic, but this is just a nice cartoon, I think, to orient yourself. Okay. So, Francesco?
But in this case, because you're kind of have one excitation per molecule, you kind of like impose a particular conservation law. Is that
That's
like...
right. That's right. You're absolutely right. There's a conservation law. There are actually a lot of conservation laws here. From the interaction alone, forget the tunneling terms. If I just had the interaction term alone, you'll see that the number of particles per column on this drawing is conserved, right? Because I cannot tunnel in real space, only in synthetic space. And more interestingly, the number of particles per row is also conserved because this flip-flop doesn't change the total number in a row. This is actually something known as a subsystem symmetry. And if you've ever studied fracton models, one of the hallmarks of all these fracton models is that they have a subsystem symmetry. And so I'd mentioned there were hints that this might be connected to fractons. You've actually hit on one of the very important ways that may be the case. Do notice that the conservation of the number per row gets broken if you turn on the synthetic tunneling. The synthetic tunneling just lets the particles move up and down in this picture. And so that's no longer conserved, but you still have the column conservation. Yeah, great question. I mean, this is something we're really trying to come to grips with. And you do have to be careful. I mean, this is actually something, look, if you didn't have this conservation, the ground state would be all the particles just live in the lowest energy state. I mean, in the rotating frame, it's all degenerate. It's not really the lowest energy, but in the lab frame, at least it would just all live in this state. And that's not what happens because you have this conservation. That's precisely why it can't relax down to the ground state. That's why the rotating wave is okay. Yeah.
I guess what you're emphasizing that there's interesting physics in this direction, but is there also mechanisms in which you can like allow the synthetic and real dimension to kind of like interact more? Because like, for example, we know like stuff like gauge fields needs the particles to hop in.
Yeah, it's a very good question. I mean, so the answer is you could probably think about it, letting these things move around in real space a little bit. And you could even, I mean, especially like, maybe you could make a ladder in real space so that even if they don't actually tunnel, you can kind of effectively make them tunnel to make gauge fields and things. But this is not something we've thought a lot about. If you have great ideas, let me know. I think this could be really fun. And maybe I'm too pessimistic. There are these things, non-reactive molecules that don't react. We've avoided it because non-reactive molecules empirically look like they do react. And I'm sure that's something we'll hear a lot more about. I mean, I think June said a little bit, but Conquin later in this week. So I've been reluctant to look at that. Also, Rydberg atoms, there have been really interesting physics looking at Rydberg dress systems where there is some motion simultaneously with the Rydberg interactions, and Wasim has done that. So maybe you could use those techniques. But because I really want to get to something that's sort of experimentally realistic as soon as possible, we've been putting those things off. If I had twice as many people working on it, these are things we'd be thinking about. So feel free to volunteer yourself. So how far away are we from having interacting systems like this? And I am just including this slide because it's connected to Boulder and it's connected to some work I've done, and it's connected to our lecturers, Jun Yi and also Anna Maria and Debbie Jin have done, where they did experiments on ultra-cold molecules and optical lattices, and they saw the effects of interactions very clearly. Okay, and they were using a synthetic dimension. Now, they never used the word synthetic dimension. We never used the word synthetic dimension in these papers because the synthetic dimensions only had 2 lattice sites. So it was very natural to talk about this as a spin 1/2 model, right? Each molecule had 2 states. That's a spin 1/2. It's interacting spin 1/2. There's no point in dressing it up with this fancy synthetic dimension language. But it means the physics is there. It demonstrated the coherent internal manipulation of those 2 levels and the interactions of this flip-flop type between them in the molecules. And so, there's, adding those different microwaves to access other levels, it's really no more difficult. It's just doing the sort of things that Simon Cornish has been doing with the internal levels at the same time as you do an experiment like this. But there's no incompatibility between these 2 things. And with Rydbergs, there's been a lot of work on spin models and Rydberg interacting models from Marcus Kreiner, Vladan Vuletic, Misha Lukin, Emmanuel Bloch, Wasim Becker, Antoine Broves, all these people have done these things. So there, I think there's also no fundamental barrier to combining those techniques with what I just demonstrated to you from Tom's group. And in fact, Tom has an experiment doing this, and Bryce Gadway has an experiment doing this they're working on. And I've been talking to Manuel Andres. So I think this capability really is really coming online. Now, this comment I made may give you some skepticism. Oh, and there's a comment in the chat, maybe this is the skepticism. Okay, no, this is a different comment. We'll come back to my skepticism in a second. So Garrett says, what does it look like for the interaction to get weaker with distance? Does the excitation exchange occur more slowly at longer distance? Okay, so Garrett, do you mean in real space or in synthetic space? And I'll wait for you to. I guess I can start answering while he's typing. So in real space, okay, he wants synthetic space. So in synthetic space, the point is that the dipole matrix element, so it's, remember this is coming from, see how fast I can flash back to the, this diagram. So remember that this interaction is really just a dipole-dipole interaction. It's like d dot d over r cubed, 1 minus 3 cos squared theta, right? But it's that d dot d that's critical. So it's d, the dipole operator of the first molecule, times d, the dipole molecule operator of the second molecule. And so that d operator can only increase or decrease the angular momentum by 1 unit. So I can't possibly flip-flop at longer range because those d operators just can't change more than 1 unit of angular momentum. If I wanted to turn such things on, you can actually do it by dressing in different states, so that what I'm calling in here is really a superposition of n and n plus 2 and n plus 3. Then you can do things like that. But at least naively, you'll just get the sort of nearest neighbor in the synthetic direction. And in the real direction, so in the physical separation between the molecules, it decays like 1 over r cubed because of the dipole interactions. So if I have these two traps and I just move those traps further and further away, it decays like 1 over r cubed. And then there's some spatial anisotropy from the 1 minus 3 cos squared theta factor. In all the mini body calculations I've done here, we have actually treated the real space as nearest neighbor, which is probably a really good approximation for 1D. 1 over r cubed is a pretty fast decay in 1D. Maybe not so great in higher dimensions, but I still think it's a good starting place. Shah is asking, in synthetic dimensions, can you get long-range correlations? Yeah, absolutely. So it depends a little bit how you want to define correlations, of course. In some sense, there's a correlation, which is what Francisco said, which is once I know there's one particle on one site, I know there are no other particles on any of the other sites. Now, that's a very, from the viewpoint of what's actually going on in the experiment, that's a very trivial kind of correlation. But I'll show you the kinds of correlations you can get. And they really are, I would say, in a combination of the synthetic and real space. The correlation structure is precisely what I want to discuss now. So let me just show you what happens. And what happens is very intuitive.
I have a question.
Yep.
Sorry, I guess I didn't phrase my question very well.
Oh, sure.
But I guess what I'm imagining is when you have these two molecules in a proximity to one another, and if they're in states of opposite parity, then they do this dipolar exchange interaction. And I'm imagining them as swapping this excitation. And if they're at a close distance, then I'm guessing I'm associating this exchange with a certain speed, like a certain frequency of this flopping. And I'm wondering at larger distances, is this speed getting slower?
It gets slower, and it decays exactly as 1 over r cubed. So, so if I double the distance between them, I'm 8 times slower. And that's precisely this just dipole interaction. And this is actually something that's been quantitatively probed in the experiments that wherever I showed these experiments. So I did show them good here. So if you go look at this Nature paper here, the analysis of this data shows very clearly, actually, I think it's more clear in the PRL here, which it looks like an experimental PRL I'm first author on, which is kind of awesome. But anyways, in this PRL here, you'll actually see an analysis which convincingly shows that you have contributions to those flip-flop processes that are exactly for nearest neighbors in the lattice site 1, for next nearest neighbors, at least in 1D, it would be 1/8. For the next one, it's 1/27. Of course, it was a 3D lattice, so all the numbers are more complicated, but that structure is seen out to quite long range interactions.
Okay, thank you.
And so that's going to be really important in the experiments. Like I said, for a starting point of calculations, we didn't mostly include this because it makes life a lot harder. So we pretended it was nearest neighbor, but I think that's a decent starting point. Okay, so what do we expect for the correlations? So if all we had was tunneling and no interactions, and let's just think about two molecules, right? So how are we going to figure out many molecules? We're going to start two, and then we're going to grow. So two molecules, no interactions, they can just delocalize in the synthetic dimension independently. Right, so it's like if the synthetic dimension is vertical, you just have these two particles independently going up and down. The dipole-dipole interaction actually binds the molecules into a dimer of molecules. And the reason here is also easy to see. If the molecules are far apart in the synthetic space, they won't resonate. If they're close by, they do resonate, right? If they're nearest neighbors in the synthetic space, they can resonate. And in quantum mechanics, when you can resonate between configurations, it lowers your energy. So the particles are going to want to sit close together rather than far apart. So as I turn up that interaction strength, I expect to go from this thing where the two molecules are independently moving up and down in the synthetic dimension to where they move locked together. And I just have this dimer moving up and down. So we went and you can exactly solve the two-particle problem, and that is indeed what happens. Let's think about how this goes on to the many-body problem. And the many-body problem, well, if the first molecule wants to lock hands with the next molecule, they form this dimer. Now the second molecule wants to lock hands with its neighbor. That's kind of this 3 in a row configuration. Now the fourth molecule locks with the third, fifth locks with the fourth. You can see it's like holding hands with your neighbors. And so what happens is at no interactions, I just have this tunneling. It's like an abacus of all the beads independently moving up and down, and I don't care what the other beads are doing. But as I turn up the interactions, the beads all lock together and form a string. And hopefully what I mean by string is clear here. If I'm thinking one real plus one synthetic, I go from these particles just making a gas in this kind of two-dimensional region to where they lock together and really make a one-dimensional object that can float around inside that two-dimensional space. Just like this picture on the right, you have these wires living in a higher dimensional space. And, and that's really the whole idea. That's all I mean by a string. So Eduardo has a question: how do the correlations get affected by motion of the molecules in the lattice site where they reside? Thinking of possible decoherence. That is an extremely good question. So a student in my group has been working on this just for the spin 1/2 case. And this does seem to be a very serious source of decoherence for a lot of these Rydberg quantum simulation experiments that has not been addressed. It's very difficult to get theoretical handle on it, but I think we have a good enough handle that we know it is a limitation. That said, it's not the dominant effect. And so I do think you can see, it doesn't start to play a role until you get to very large systems or very long time evolutions. Now, there are two things. One is the kind of back action that when two things get excited into Rydberg states, it causes them to vibrate, right, in the lattice sites, or maybe even eventually get expelled out of the lattice. The other thing is just that initially, maybe these molecules weren't cooled to the ground state on each site, right? Maybe there's some vibrational excitations. And actually in a lot of Rydberg experiments with the tweezers, that's common. You don't get all the way to the ground state. You work in a superposition of the few lowest lying vibrational states. And it turns out that it's pretty insensitive to that type of motion. The physics I'm claiming here, the Hamiltonian, is pretty insensitive in the microtrap experiments if you have 1 or 2 thermal excitations. But it would start to make me nervous if you had more than that. Basically, if you're in the kind of regime where people are doing good stuff with spin models, it should also be good for these types of synthetic dimension experiments. But you do have to be pretty cold for that. So Shah asks if the math looks like dimerization. Yes, at the 2-particle calculation, it's exactly dimerization. And in the many-body case, you can actually capture most of this structure using a BCS wave function, pretending it's fermions in a 2-dimensional space. There are some caveats to those statements, but so we approached this first with a few types of mean field theory, including that one, which gave this structure, but then we did some more sophisticated things. So let me tell you about the more sophisticated things. This simple picture is in fact correct. And the first indication of this came with DMRG. There are a lot of curves here, but all I want you to take away is this is the tunneling divided by interaction on the horizontal axis. And you see there's clearly on the right here, this is the width of the string I'm plotting, that there's a pretty good width. And then as I go to the left, it dips down and the width looks like it's scaling to 0, at least in some region. And so what's going on here is that where the width is 0 relative to the synthetic dimension size, that's where you've formed a string. Things have collapsed onto a finite width thing out of an infinite synthetic dimension. And where it's non-zero, it means it's just floating around and sort of delocalized.
Can I ask something?
Yep.
So I guess you have this in the synthetic dimension, there's this staggered order. That's what you have drawn.
That's
so
a very
where
good
does that,
question.
and so where does that happen? And like in the synthetic dimension, that can happen anywhere, right?
Yeah, there's a translation symmetry here in the synthetic direction that gets spontaneously broken. And then there's an order that you're talking about, which is this staggering, which is, I guess you might naively expect it goes like n+1, n+1, n+1. Actually, it's more interesting than that. And this is something which we're only beginning to uncover. I'd say there are major questions about this, and this is something that makes the problem really interesting. So we found an exact solution of this when you turn the synthetic tunneling off and when you are in 1D. So you just have the flip-flop interaction and nothing else. And you actually get a much more interesting solution. And the solution is, sure, I could go n+1, 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 but just intuitively, couldn't I do n+1, n+2, n+1, right? So it turns out, and takes some effort to show, all of the ground states are 3 sites wide. So there's a huge degeneracy of ground states. In fact, in that special limit, it's an exponential degeneracy of ground states, also reminiscent of fractons, if you're familiar with that. And all of those ground states are 3 sites wide, or they could be 2 sites wide in special cases, right? If they just zigzag back and forth. But generically, they're 3 sites wide. Everything that's 4 or more sites wide is gapped in energy, or at least higher in energy, maybe not gapped. So the structure is very intricate, and there's a lot of dynamics. So you have this spontaneous symmetry breaking of making the string, but then there are all these dynamical degrees of freedom that live on the string, and we don't understand those very well, except in this one extremely special limit. Yep. And so I've got 8 minutes here. Actually, that's good. So let me show you. This is a string. We have, for the first time just in the last week or two, some collaborators have studied this, and I'd say with better numerics than we were able to do with the DMRG here. We were able to both tackle finite temperature, and we were able to tackle the 2-dimensional system, so 2 plus 1 dimensional system. So a 3D system where I have 2 real space and 1 synthetic space. So what's the analog of the string there? Well, it's a membrane. I have a 3-dimensional space, and now I grab onto all my neighbors in the 2 real directions, and I collapse down to a sheet, just like that. And so Chun Hun Fan, a grad student at UC Davis with Richard Scalatar, has done these calculations. And this is a plot, again, of some measure of the width of the string as a function of temperature for various parameters we can talk about if you care. But what you see is that at high temperature, the width is very wide. And then as you lower the temperature, there's some fairly sharp feature where it goes into this string state. So, and when you do the finite size scaling, this sort of width, as you make the synthetic dimension bigger, well, it gets wider and wider in the delocalized phase, whereas it stays nice and finite in the localized phase, suggesting it really does have this membrane structure. There are a lot of subtleties about this. I could probably talk about this data for 45 minutes, so I'm not going to say too much about this, except to say this is the first time we've really been able to convincingly show, I think, that there is a transition, especially in these higher dimensional systems. And we have lots of data like this. It's not just this one plot. Now, where the real mysteries are is where I've alluded to. What makes all this stuff interesting? Making a string is pretty interesting, but maybe it's just translation symmetry breaking. Maybe it's very simple. Well, I think you can be talked out of that point of view pretty straightforwardly by thinking about what happens as you go through the phase transition. So as you go through the phase transition, the string gets fatter and fatter and fatter, right? So the width of this string, I said, was 3 sites in this special limit. But as you move away from this limit by turning on quantum or thermal fluctuations, the string gets fatter and fatter and fatter until it totally delocalizes. And we have a simple picture in the one special limit I told you about. It actually corresponds to, you have a string that can fluctuate, and there are 2 types of particles, of hardcore bosons and hardcore anti-bosons, that live on that string. And that's the effective field theory of the system in that one very special limit. But how that gets modified as you go to this phase transition, what other orders are there, what their field theories are, their universal properties, we have no idea, right? So this is all just ripe for a study. Okay, that's all I'm going to say. Somebody should figure it out. We've worked very hard and can't figure out what's going on. Here's another example of fun things to do with interactions. So I'm going to switch gears a little bit for this one. So this is not about the strings, which is really about letting the system find an equilibrium state in the synthetic dimension with interactions. Instead, I'm going to dynamically prepare all of the particles and edge states. And so here's a cartoon of one real and one synthetic with SSH. And if I want, I can just, it's straightforward to put all the particles in the edge states initially, and you'll see they can live a long time. You can do a Fermi's golden rule calculation. The dipole-dipole interaction will kick them out of the edge states eventually, but that can be very slow compared to the other things going on. And so now I can just project my Hamiltonian into that subspace, since the particles are going to live there, and just project it down onto the edge states. And what am I going to get? Well, it's a spin 1/2 on each site. There are 2 edge states. And so it looks like an Ising model. And this looks like the worst possible way you could imagine to get an Ising model, right? So I went through this hugely complicated thing with the synthetic dimensions just to get 2 levels. But it has one really interesting feature. And the feature is that it's a topologically protected Ising model. And what I mean by that is I can flood the system with noise. Remember those plots I showed you that had the noise for one particle? And we showed that that edge state didn't move? Well, typically, if you have an Ising model and you apply noise, you'll turn on extra terms here. You'll turn on transverse fields, like in the many-body localization problem we were looking at. Or you can even turn on other types of interactions. But in this case, all of those extra terms are exponentially suppressed by the topology. And so I think that's cool. I don't know if it's good for anything, but it's different than anything I'm familiar with dealing with. And if you did this not with SSH, but with more interesting band structures, you can actually think of this as realizing anomalous field theories, or anomalous states of matter. So if you know, I don't know if you know what that means, but it just means there are certain quantum field theories that are allowed in nature, and then there are other quantum field theories which don't actually exist, but can occur on the boundary of something. So for example, I could have a 2-dimensional theory that can't actually exist in 2D, but it could exist on a 2-dimensional boundary of a 3-dimensional surface. And that's very common, and you know, these sorts of constructs appear in lots of topological phenomena. And these are known as anomalies in the high energy physics and field theory literature. So what happens is you can actually use the synthetic dimension as an extra dimension of space and realize edge states that are anomalous field theories. And now by making a row of these in my microtraps, I can couple these anomalous theories together. And so I think that's fun. I don't know what you could do with it, but it's something worth thinking about. And that is more, I have one slide, and I guess, yeah, if you'll indulge me, I have 3 minutes left, so I will talk through the slide. I want to hint at this fractons that I've mentioned a couple of times. So there, if you don't know what fractons are, there was an article in Quanta magazine today, if you want to go check it out, and it was pretty good. You know, everyone was rapturously saying how exotic these things are, which I guess that's a good thing. But there are hints that this actually is a fractonic model, even though we wrote this before fractons were really a thing, so we didn't realize this. So this subsystem symmetry is one of the ingredients in a lot of fracton models, and we've seen that we have this independent row and column conservation here. Another common feature, not just of fracton models, but lots of topological models, like real topological order models like Kitaev and these things, is that they have 4-spin interactions. And actually, maybe I won't tell you here, maybe you can figure it out from the picture, but there's a different sort of way of viewing these synthetic dimensions where this dipole-dipole interaction actually looks like a 4-spin interaction. So without any engineering, you're naturally getting a 4-spin interaction, which are otherwise a nightmare to generate experimentally. And so we can talk about that if you want. But I think let me just jump to my conclusions. You know, synthetic dimensions are this real vast frontier of simultaneously controlling internal and motional degrees of freedom that are, I think, going to let us do a lot of new things, and which really look very different from systems that occur just in real dimensions, or these sorts of synthetic dimensions in molecules and Rydbergs look very different from the types of synthetic dimensions you get in Ian's experiments. And so I've shown you some examples of that, of what you can do with single particle physics, what you can get with strings, what you can get with these sort of anomalous theories coupled together with the topological. But I think the most fun stuff is still awaiting us. So listening.
All right, thanks, Kadden. So I'm going to take this chance to ask the first question. So for the students in the audience, if they were to guess like what they should jump out and do tomorrow along the directions in which you're more confident that you're kind of right, as opposed to more confident you're kind of uncertain, and where the best directions for the highest degree of uncertainty would be, where should they jump in to make the biggest impact?
I think if I was going to work on one thing, and so maybe this is something which we are very actively trying to ramp up, but haven't really worked out, is using this new mapping in terms of thinking of it as this four-spin interaction. What does that get us? So it's not, you don't exactly just immediately get Kitaev toric code or something, but you get something that's so close to it that I think we have to investigate this and we have to understand this. And this is tied to the whole fracton story. This was just hiding. We hadn't realized it until we started talking with some people about this. So I would try to see, is there something to this, or is this just a red herring and we're getting misled? And one very technical question, like very specific question that remains, that I think would provide an enormous amount of insight, is if I take the Kitaev model, or pick your favorite topologically ordered model or fractons or whatever, and I study it in the limit of vanishingly, sorry, not small magnetization, near the maximally magnetized state. So almost all of the spins are down. Is that state still interesting? That's not the sector that most people look at the toric code and other models, but is there still some remnant of the topology there? I think there is, and that's the limit you'd be restricted to with these synthetic systems. But if there's something there, I think there would be something immediately interesting.
All right. So thanks for everyone for indulging me asking the first question of Kadden. And at this point, are any of the students who are interested in doing fantastic new work interested in asking questions of Kadden or clarifying things he's made?
I had a question. So in the beginning of your talk, I guess, there was this N, which was 2, 3, 4, or 5. That was SUN models. And here it seems this N is the synthetic dimension. So where do you differentiate between that? How do you draw the boundary?
That's an awesome connection. So you heard Anna Maria talk about like spin orbit coupling synthetic dimensions with the clocks. And that's kind of connected to using the strontium atom, using its internal degrees of freedom as a synthetic dimension. And there's actually been work on this from Filani, I think. Sorry, I'm blanking on that reference. I'm sure it's Filani. I'm just trying to remember the details of what they did. But they've actually used these internal states of alkaline earth atoms as a synthetic dimension. And now you can couple those by Raman lasers, just like Ian does for rubidium, where using Raman lasers to couple these, and you can make gauge fields and spin orbit coupling and all kinds of stuff. So, and one thing I do like about this, I didn't really make this point, but both of the topics, both the synthetic dimension and the SUN, I think can be viewed as really pushing both the internal state control and the motional control. So the SUN with strontium, you've got 10 states to work with. That's just not the kind of size of internal states that we've typically been using in cold atoms. And so I think it's fun as a new direction. It's also fun because there's some fundamental question, like when the number of states gets large, aren't things supposed to be classical? Right. And so why doesn't SUN become classical? That's a pop quiz for you to think about. There are very good physical reasons why the large N limit of SUN does not look classical. Whereas if I took a large N limit of SU2, remember I can have an SU2 symmetry, but I could have a large spin. And that's very different from having SUN. And if I just take a large spin with SU2, it actually becomes classical, which SUN may not. And so there are interesting things about that. And then in the synthetic dimension, is it going to become classical as N becomes large? I would argue no, but this is, I think there are deep questions there.
Yes, my question is that if for somebody who wants to dig a little bit deeper on that fracton part, do you have specific references?
No, this is all totally unpublished. Totally, it came up. I have a grant proposal I could send you. That's about the closest I could do. Real quickly, here's the entire idea of the mapping of how you get these four spin interactions. So here's on the left in panel A, here is a real space in a synthetic space, just like we've been talking about a lot. And there's some particles sprinkled in here. And if you ask, what does the dipole-dipole interaction do? Well, it says that when this green particle on the left goes down, the one on the right has to go up, right? It's just this flip-flop. But now I'm just going to make a mapping where I'm going to look at this same two-dimensional, one real and one synthetic dimension lattice, as a set of spins. If there's a particle there, I'm going to call it spin up. If there's not, I'm going to call it spin down. And now this flip-flop interaction, that's what I'm drawing here in B, looks just like a spin exchange interaction, sigma plus, sigma minus around the plaquette. And you probably know that many of these topological models have this type of spin interaction structure. And so that's where I would start. Just given this structure, which is slightly different from normal things like sigma x, sigma x, sigma x, sigma x, but has a lot of similarities with it, can you still get the same physics you'd get from toric code, for example? But no, I don't have a reference for you.
Interesting.
Okay, are there any last minute questions for Kadden? Because unlike the speakers for tomorrow and later on this week, this will be the last obvious context to pester him with really important questions.
Yeah. Eduardo is taking the chance to ask me, since he never has another chance to talk to me. He's my grad student. So he's saying, are there normal modes of the strings and membranes? And the answer is, I'm in some limit, I think absolutely there are. So it gets a little tricky because the synthetic dimension is discrete. And so normally, if I think about the string wiggling, I'd want to think about it in continuous space. And if the string wiggled in continuous space, there'd be a wave equation associated with normal modes and things like that. Now, because the synthetic dimension is discrete, you have to be careful with this. However, at least in the limit where the string gets fat, so it's not confined to these three levels, but I turn up the thermal or quantum fluctuations, so it averages over a lot of these levels, I think it must reduce back to just quantum theory of a string. So there would be normal modes and everything. Yeah, it's a good question. It's a sort of emergent real, not just periodicity, but continuous translation symmetry.
I have a question. Going back to the phase diagram for a 1D string, you said there was like 3 phases. What are the 2 with the bound states? Like,
yeah,
what's the
that's
difference?
very good. So I don't think I said it, but my slide said it, so I got myself into trouble. There are 2 bound state phases. There are 2 string phases, and the reason has to do with this dimerization. So at the 2 particle level, depending on whether my dipole interactions are attractive or repulsive, I get different symmetries for the dimerized. Think about the relative. Hold on. Did my screen freeze? Oh no, you're okay. So if I think about the relative wave function between the 2 particles, I could either get a parity symmetric wave function for interchanging the 2 or anti-symmetric, right? And so that's 2 different characters of bound states. If you think about it, you can think about like an S wave and a P wave bound state, although it's 1D, so it's just symmetric and anti-symmetric. And so I won't say it out loud because I'll probably flip my signs around, but one of these string phases is the anti-symmetric and the other is the symmetric. Interestingly, QMC is only sign problem free. On the next slide I showed you QMC, it's only sign problem free for one of those signs. So we understand it much better than we understand the other sign of the interactions.
Maybe one question back on the SUN stuff. Is it known, for example, for SU4, if I have 2 particles per site, if there's like an interesting ground state, or like at SU3, if I have 1.5 particles per site? Is that?
Yeah, okay. Super question. So what happens if I'm at other, I guess you're mostly concerned about integer fillings. So I have 1 or 2 or 3 or 4 particles per site.
Yeah.
So if you think at least in the spin limit, the Heisenberg model limit, so U over T is very large and integer filling, then what these correspond to are Heisenberg models in higher representations of the SUN group, if that means anything to you. It won't need to be for the rest of this response. But so 2 particles per site corresponds to the second representation of the SUN model, and so on. So I can tell you what's known. We don't know a lot about most of those, but there are special cases we know. So back in 1989, I think it was Reed and Sachdev studied a model in 1D where what you had is you had even sites in your lattice had 1 particle per site, and odd sites had n-1 particles per site. Okay, and to understand this special choice, you have to understand something about the SUN symmetry. So to make a singlet, by which I mean something that's invariant under the symmetry group, you need n total particles. So when you construct it in this way, pairs of sites can dimerize to make a singlet. And so they were actually able to show that you get singlet on this pair, singlet on the next pair, singlet on the next pair, analytically in that limit. And then the large N limit becomes controllable. So at least for large N, they were able to show this. Now, this computation I've cited here by Mike Hermele, Anna Maria, Victor Guerrari, they studied another funny limit where you need a finite number of sites to make an SUN singlet. So for example, you could take n to infinity, but you also take the number of particles per site to infinity, and you keep the ratio fixed. And what this does is you can fix the number of sites needed to make an SUN singlet. And so you can do this for, so this is a special, sort of infinite filling limit where it's taken in the right way. So when you do that, there you can show exactly what the ground states are for 2 sites to make a singlet, 3 sites to make a singlet, 4 sites to make a singlet, and 5 sites to make a singlet. For a 2, 3, 4, you get symmetry breaking patterns, not exactly what you see here, but other symmetry breaking patterns. For 5 and above, they prove that you get a chiral spin liquid. And it's actually the only provable, maybe I shouldn't say this, but what I wanted to say is the only provable model with a chiral spin liquid where with only nearest neighbor interactions. So they proved that some exotic type of mean field theory called the slave fermion theory becomes exact in the large N limit. So then they're able to solve that mean field theory. Yep.
Thank you.
Mm-hmm.
All right, so since it's getting late, I think it's time to say sayonara to Kadden, although I suspect he'll be around throughout this week. Tomorrow's schedule mimics today's schedule, with the exception that there will be no research seminar at the end of the day. So you can expect continued lectures from the previous people. Are there any scheduling or organizational questions you guys might have before we sign off for today? All right, so if that is not the case, then I'm looking forward to seeing all of you tomorrow at 9 a.m. Boulder time for the second talk from Emmanuel Bloch.
Thanks, everybody. See you tomorrow.
See you guys later and have a great evening, and ponder